In this video we're going to look at vectors and scalars. This is a really important foundation for equations of motion, projectile motion and momentum that we're going to come on to look at. These are what I want you to be able to do. I want you to be able to state the difference between a scalar and a vector, calculate the sum of vectors when they're parallel, and then also be able to calculate the sum of vectors when they are at right angles to each other. We're going to work through each of these skills individually and then review the whole lot at the end. First off, I want you to think about this problem. You're on a train travelling at 40 meters per second when you pass another train that's travelling at 20 meters per second. When you look out at the other train, how fast will it appear to be going? There are two common answers to this question. They are 20 meters per second and 60 meters per second. The direction of the two trains is clearly really important. Think about it again, and instead of looking at how fast the other one's going to be travelling past your window, imagine the two trains are colliding. They're both going in the same direction at different speeds. This clearly would have a very different impact than two trains that are travelling in the opposite direction of these two speeds. What I'm trying to get you to think about here is that in a lot of physics problems, the direction things are moving or being pushed is really important. We start with scalar quantities. For some things, we can just measure them and we have a value, we have a size. 100 kilograms, for example, or 20 degrees. This could be bigger, it could be smaller. Direction isn't considered here. Where we just have a size or a magnitude, we call it a scalar quantity. Now I want you to be able to tell me the difference between a scalar and a vector. As such, I need to tell you what a vector is, and you should be able to compare the two. With a vector, as well as it having a size, a number that you can apply to it, there's also a direction that you need to take account of. Common vectors that you'll have come across before would be velocity, which is speed in a given direction, and force. The direction of a force is really important as to what will happen to an object. So some examples here, if we've got a car travelling at 100 kilometers an hour, that would be a scalar. If you know the direction it's travelling in as well, 100 kilometers an hour south, that would be a vector. Now we're moving on to calculate the vector sum of parallel vectors. That may sound complicated, but let me show you simple. At first, we've got a rule that we need to try and stick to. Before you work out any of these problems, I would choose a positive and a negative direction. For me, usually, up and to the right would be positive, and anything moving down or to the left would be negative. Doesn't matter which way you choose, but you need to make sure you're consistent with it. You stick to it throughout a problem. Let's look at a problem. We have two vectors here. Imagine you're watching this from off of this walkway. The walkway is moving past you at 2.5 meters per second. The man who's on it can choose to walk or not walk. We can add the two vectors together to work out how fast he may seem to be moving past us. Now, I said pick a positive direction. In this example, he's moving to the right. So, we've got both numbers being positive. To add vectors that are parallel to each other, all we do is add them together. So, what do you get if you add these two vectors together? 1.75 plus 2.5 meters per second gives us an answer of 4.25 meters per second. This is how fast the person would seem to be moving past you. We said that both of these vectors were right, so the resultant vector would be 4.25 meters per second to the right. The best way to check if we understand this would be to see what would happen if the man travelled in the opposite direction. We picked right as our positive direction, so if the man was walking to the left, he would be travelling with a velocity of minus 1.75 meters per second. We still add the vectors together. If we add 2.5 to minus 1.75, we find that he seems to be moving past us with a velocity of 0.75 meters per second. The number is still positive, which means he must be moving to the right, but he seems, relative to the person who's not on the walkway, to be moving much less quickly. Here I'm going to give you a couple of problems. They're going to test your understanding of what we've just talked about. The first one, we have two forces pushing in opposite directions. In the second, we have the same two forces, but the direction of one of them has changed. Pause the video and work out the resultant vector. So, what was the solution? Remember my first step? Choose a positive direction. Now in this we've only got left and right. We don't need to worry about up and down. So I've picked right as being positive, left as negative. Bring the first problem up. We have minus 400 newtons, add 300 newtons. Left was negative. If we add minus 400 to 300, the resultant would be minus 100. So the resultant is minus 100 newtons. As it's negative, that means it must be moving to the left. In the second example, both values would be negative. So minus 300 add minus 400 would give us minus 700, or 700 newtons to the left. Did you get that right? Finally, we need to be able to find the resultant of vectors that are at right angles to each other. This is a bit trickier. We're going to look at two different methods to work this out. One of them is to use a scale diagram, and the other one is to use a calculation. We're going to start with a scale diagram. A statement at the bottom of the screen may seem obvious, but this is really important. You have to draw a scale diagram to a scale that you have chosen. For example, if you were choosing velocities, you may choose that for every centimetre you draw a line, that represents 5 meters per second. Doesn't matter what the scale is, as long as it's sensible for the size of paper you're using, and that you stick to that scale. So let's say we've got two vectors. We might have a first vector, and you draw an arrow to represent it, to scale. For example, this could be 25 meters per second, and you draw the line 5 centimeters long based on the scale that I talked about earlier. Now, this is just one vector. We've got two vectors, now at 90 degrees to each other. So we draw in our second vector. You can clearly see from the scale diagram, this second vector, this second velocity, for example, must be smaller because the arrow is less long. Maybe it would be 1 meter per second or 5 meters per second. Certainly not the 25 meters per second we had going horizontally. There's an important note here. It says attach head to tail. If we look at these two velocities, it's clear that the object is travelling to the right and up. By attaching them head to tail, when we draw in the resultant vector is going to the right and up, which is the same as the two vectors individually. So we've drawn in our resultant here. Instead of doing any calculations, this scale diagram has allowed us to work out this resultant vector. It could be a velocity, a force, whatever you're being asked to do. To work out its size, all you need to do is measure its length. You then just use your scale to work backwards to work out whatever the resultant velocity must be. Now, as it's a vector, we said direction was important. At the moment, you just have a scalar, a size. As such, you also need to work out its angle. You'd measure this with a protractor. This is our second method for working out the resultant of two vectors that are at 90 degrees. This animation very neatly shows a mathematical principle we should all be familiar with. Pythagoras' theorem. Clearly you can see that if you square this side of a triangle and this side of a triangle, it exactly equals the square of the larger side of the triangle. This is just a nice proof of this. We're going to use Pythagoras' theorem to work out the resultant side of this triangle instead of having to draw it out. This is our second method. So if we had a vector travelling right and a second one at 90 degrees to that, we can work out the resultant. So this thing is clearly going right and up. The resultant, which goes right and up, can be worked out using Pythagoras' theorem. Just to remind us, a squared equals b squared plus c squared. Here's an example. An object is travelling at 15 meters per second up. It's also travelling at 30 meters per second to the right. Now, the rule that I gave you earlier still applies. We need to attach these head to tail. As such, when we draw in our resultant, it travels up and to the right, and the two individual vectors we were adding were going right and up. This is clearly the direction the object would travel. Okay, we now just put the numbers in. So b squared plus c squared would be 30 squared plus 15 squared. That equals the resultant squared. It's important to remember that this is squared. If not, you may find you get an incorrect solution that's far too large. So 15 squared plus 30 squared equals the resultant squared. As such, the resultant equals the square root of 15 squared plus 30 squared. That is, in this example, 33.54 meters per second. We're not done yet. This only has a size. It doesn't have a direction. Therefore, this is a scalar. We need to work out the direction. For this, we need to use some trigonometry. You should remember SOHCAHTOA. The sine of an angle equals the opposite over the hypotenuse. The cosine of an angle equals the adjacent over the hypotenuse. And the tan of the angle equals the opposite over the adjacent. For all of these problems, as you're given two velocities or vectors of any kind at 90 degrees, you're always going to have the adjacent and the opposite. So we're going to pretty much jump to tan all the time here. We know that tan of an angle is equal to the opposite over the adjacent. To work out the angle, all we need to use is the inverse tan function on your calculator. So the angle equals inverse tan of this fraction, which 15 over 30 was 0.5, which gives us an angle of 26.56 degrees. So our resultant vector is 23.54 meters per second at 26.6 degrees from the horizontal. This is a vector because it has a size, a magnitude, and a direction. We said earlier we need to be able to do these things. I want you to have a look through this list. Can you do these things? Can you tell me what the difference between a scalar and a vector is? Can you calculate the vector sum of two vectors that are parallel? Can you find the resultant of vectors that are at right angles to each other? Let's test that third one. Pause the video and have a go at this question. The solution will come up in a second.